So chapter 6 extends beyond just triangles, and we start to look at polygons. So a triangle has three sides, would be a polygon with three sides, and then we're going to look at all different possible values of sides of polygons, all the way up to 100 sides, if we want to think about it that way. But one of the most important things we learned when we studied triangles, the most important properties of a triangle, was the sum of the interior angles. Right? If I take these three angles here and I add them up, we should know right away that they always add up to 180 degrees. Right? The sum of any three angles in a triangle always add up to 180 degrees. So now what we want to start to think about, and we did look at quadrilaterals already in there, what happens if my figure now has four sides instead of three? So what I've done is I've added a side. Well, watch this. Notice that I have two triangles, right? So that would be 360 degrees. So I've basically added another 180 degrees, right? 180 degrees in this triangle, another 180 degrees in this triangle. Let me just do it one more time, and then I think we'll kind of have the basic idea of the property. I'll try to draw a pentagon here. And I'm going to do the same thing. I want to attach some vertices, but I'm going to do it as many times as I can, you'll notice. I really don't have any other way to attach vertices here, and you'll notice how many triangles I have now. 1, 2, 3. So that's going to be 180 times 3. This was 180 times 2. So in terms of the number of degrees that are in that particular polygon. So every time I add a side, I basically added a triangle in that interior. So you notice this number 180 in our formula. So when we have three sides, 3 minus 2, right? A triangle has three sides. 3 minus 2 is 180. So that's 1 times 180. And that's our 180 degrees, which we've known for a while. When I had four sides, I take 4 minus 2 times 180. So this is 2 times 180. And that's our 360 degrees, which we've seen before. And I'll do it one more time if I had a five-sided figure, because the pattern will just continue on and on. This is going to be 3 times 180, because I would have three triangles in that situation. So I don't want to draw the polygon every time, and I don't need to draw the polygon every time. What we do is we observe this formula that comes about from our triangles, right? However many sides I had. So I don't want to have to draw a decagon, which is a 10-sided figure, right? To see what the sum of the angles would be and count how many triangles will be in that. I'm just going to simply note that this is 10 sides since it's a decagon. And this is going to be 10 minus 2 times 180 when they want the sum of the measures of the interior angles. So this would just be 8 times 180. And we use our calculator at that point. So that would be 1,000. Oops. So if we drew a decagon, we could also see that there would be 8 triangles in it, and that would be 1,440 degrees. 16gon. We don't have really a fancy name for that. We just know it's 16 sides. So we're going to take 16 minus 2. That's how many triangles we'd have. That would be 14 triangles. And multiply that by 180. That's 2,520 degrees. Okay. If my polygon had 30 sides to it, this would be 30 minus 2 times 180. So that means we'd have 28 triangles in that polygon. And 28 times 180 is 5,040 degrees. Octagon, 8 sides. So this is 8 minus 2 times 180, which is 6 times 180. And again, we let the calculator do the work for us at that point, and that's 1,080 degrees. 12-sided figure. So this is going to be 12 minus 2. This is also called a dodecagon. Not to confuse anybody. The decagon has 10 sides, but if we say dodecagon, that's 12-sided. So 12 minus 2 times 180 is 10 times 180. And don't actually need a calculator for that. I'll just add a 0 to that, and that'll be 1,800 degrees. And then finally, we take 35 minus 2 times 180. 33 times 180. Be very hard to draw that. 33 triangles in there. 5,940 degrees. And two more things we're going to look at in this section. We'll think about solving some algebra here, but then also the exterior angles, which is going to be a really, really simple proposition for us. But here, the first thing I want to observe is what should these angles add up to? Because I have all these values of x, all these expressions, none of them are equal to each other. It's not in any way a regular shape. So let's see how many sides we have. We have 1, 2, 3, 4, 5. So that means the sum of the angles of this polygon should add up to, and when we had triangles, they would just add up to 180. Well, this is a pentagon, so this is going to be 5 minus 2 times 180, or 3 times 180. Okay, we need that to start. We need to know what these angles will add up to, and then that gives us an equation to work with. So these angles should all add up to 540 degrees. And that's the idea here, is to try to find a value for x. We want to solve for x. So now I'm going to just simply write that in terms of x. I have these 5 angles. 7x plus 4x plus 5 plus 5x minus 5 plus 6x plus 10, and then finally plus 4x plus 10. So we'll double check, make sure we got 5 angles there. 1, 2, 3, 4, 5, and they are 7x, 4x plus 5, 5x minus 5, 6x plus 10. This little section here gets a little busy, hard to look at, and then 4x plus 10. So it looks like I have them all, and they all add up to 540. So we have to just be careful here in adding our like terms, combining our like terms. But if we take the x's first, let's see how many of those we have. 7x and 4x would be 11x, plus another 5x would give us 16x, plus another 6x would be 22x, plus another 4x would give me 26x. Now what happens with our whole numbers? Well, I have 5 and minus 5. They'll just subtract out. They'll go away. And then finally I have plus 10 and plus 10. So that would be 26x plus 20 equals 540. And that's just a pretty easy two-step equation. So we subtract 20 from both sides. It's usually a sign I did something right if it divides out evenly for me, and I think this will. So I have 26x equals 520. Divide by 26 on both sides, and we would find that x is equal to 20. And if we plug that back in, if we wanted to check, add all the angles up, they should indeed add up to 540 for us. And the last part of this section is going to seem just way too easy. Notice there's no formula at all for the rule. The sum of the exterior angle measures of any convex polygon, one angle at each vertex, is always 360 degrees. So what we're talking about here is this angle plus this angle plus this angle, plus this angle, plus this angle. They're always going to add up to 360 degrees. When we add all of them together, they always add to 360. So it doesn't really matter how many sides the figure has. If it's a decagon, the sum of the measures of exterior angles, as soon as you see it, it's 360. Well, what if it has 16 sides? What do the exterior angles add up to? They still add up to 360. And if it's a 36-sided figure, again, they'll still add up to 360 degrees. That's it. It's as simple as that. Now, for each exterior angle, if I have more sides, well, that's going to change what each exterior angle is. So this is a little bit different question, but we do the same thing every time. We start with the 360, and we just divide it evenly by the number of sides. So if I have 12 sides, I take 360 and divide by 12, and each exterior angle in that situation will be 30 degrees. If I have a hexagon, how many sides is that? It's 6 sides. So some of you need to go back. We did these back in chapter 1, and remember how many sides does a hexagon have? How many sides does an octagon have? That's important that we remember those. Chapter 6 does not really go back and review those. It was back in chapter 1 that we did that. So if I have 6 sides, I take 360 and divide by 6 evenly. That would be 60 degrees for each exterior angle. Take 360, divide it by 20. Okay, each of those would be 18 degrees. And if our figure has 40 sides, 360, divide that by 40 degrees. Okay, hepta and septa, both of these would be 7 sides. Okay, so 360, divide that evenly 7. Doesn't divide very evenly, but it's 51.4 degrees each. 360 divide by 12. They would be 30 degrees. It's a repeat. We did the 12 gon already. 360 divide by 24. 15 degrees. Dodecagon, that's 12 sides. Okay, did that already. 360 divide by 12, we know that's 30 degrees. Okay, and then octagon, 360 divide by 8, 45 degrees. So one of the reasons why, I don't know if this jumped out to you here or not, but so many numbers divide evenly into 360. And that's one of the reasons why we have 365 days in a year, why our calendar is broken up the way it is, and why we tell time the way we tell time, right? I don't know if anybody's ever wondered, why do we have 12 hours in a day instead of 10? We usually count by 10, but all of a sudden when we're taking time, we count by 12s, and it's because of the number of values that divide evenly into that, right? If we're trying to divide up a calendar evenly, right, without rounding, and it still becomes difficult, right? That's why we have leap years, right? So we have 365 days in a year, close to 360, but that would be the reason for it in terms of navigation, 360 degrees in a circle, in terms of telling time. These types of measures work out more conveniently when we don't have decimals, when we don't have things left over in our calculations.